Hey guys, just got these in the mail. Do you know what this is? It's bearings. Let's take a look. So first of all, this is what the robot currently looks like. So this is the leg that we printed in the last video, which all I did really was remove the support and screw on servos, screw on everything, put some heat inserts. And I've already learned a lot here. There's already things that I want to change. I think the biggest thing I want to change is remove supports overall. Look how ugly this looks. You can really tell where the support material was. And yeah, so first of all, that adds a step in the process. You know, you have to remove the support. Aesthetically, it looks bad. It adds sprint time, it adds material, it adds cost. Here it looks also terrible. So yeah, so I'm not happy with anything with support. So ideally we have no support and we can just, print a lot of these things really fast. The other thing that I realized, it hasn't been an issue, but it's kind of obvious that it eventually might be, is all these heat inserts are great for, removing fasteners and stuff. But I suspect that with vibrations and just usage and things moving around, eventually they're going to loosen and we might lose the fasteners there. So we might need to put nylocks or thread lock in these inserts. So I need to think about that. And there's also some design no-nos here in these parts here, where these bolts, these screws here, are actually loaded in single shear, if you think about it. Which, it's like, in software, I'm like, oh, whatever, like as long as the software works, I'll just do it. But when it comes to hardware, I'm usually like, oh, stick to the right design rules and stuff like that, because it's not a question of like if it's gonna fail or if it works. It's like, when is it gonna fail? So I think these are all pretty small things and it will be fine, just for now, but at some point I do want to fix it. Anyways, let's open this box. So if you've never opened a McMaster box, this is what it looks like. They always give you a sheet telling you what's in the box. And they also have these branded, very nice Ziploc bags, which if you order a lot of McMaster, you're gonna have a ton of these in your house, in your office, normal box. And so these are the bearings that we paid. Let's see if it says how much. Overall, all of this was around $100 for a bunch of bolts. This was probably like $50. This thin bearing here was on its own probably like $40, and then these guys are probably like 15 each. And so I was actually thinking, I was waiting for these to come in. But as I was waiting for them to come in, I was just thinking like, oh, do we actually need bearings here? Because this is plastic on plastic, and it's pretty low load. As in, like, this robot's not gonna weigh a lot. It's like 3 kilograms max, and it's not gonna be moving crazy fast or anything. So do we actually need, these $4 bearings made out of metal? I think no. It's driving the BOM cost up and all that stuff. And so I think I want to design a version of like, no bearings, or just using plastic bearings, plastic on plastic. And I think that's going to be fine. A big part of the dream is to be able to have a swarm of robots. And the only way you can do that is if you have a low BOM cost. Now, if you remember, this was the bearing that was supposed to pop in here, right? And there was that interference, and on CAD, I was like, oh, I don't know if that's going to work. We might have to slice this part, like pause it mid-print, insert the bearing, and then continue printing. So, well, I'm gonna try to pop it right now. And yeah, it's not going in. It's not even close. So I don't have no clue how those guys did it. But again, open source guys, open source projects. And then the other two bearings here were these ones here. Okay, first of all, yeah, I'm gonna have to reprint that for sure. You can see this bearing, it's basically 2 washers and 1 washer with these kind of like bone inserts. Looks like maybe bronze. And that's, we have 2 of those, 1 for each side. And yeah, this looks nice. This looks very, very nice for sure. But it looks expensive. Let's see if I can find an Allen key for this guy. That's not it. Yeah, so now I'm just gonna try to assemble this guy. Obviously, we're gonna have to reprint this guy so we can fit the reprint the cam so we can fit the bearing in there. I've never done that, so that's gonna be interesting. But let me just see if we can actually, if everything's done with these two bearings. Stuff that needs to be printed again, I can do that tonight, like right now. Yeah, that's very nice. These washers, as I call them washers, they're obviously more than washers. They have a nice groove, and so it fits like that. And it's a little unstable. As in, like if you flip it the wrong way, it's gonna drop. Right. So assembly that is a bit of a pain. So that's another thing I would change. Right. You want to make it as easy to assemble as possible. A hard assembly, it's not just a hard assembly. It actually also adds cost technically. The more time you have to spend assembling, that's more time you gotta pay someone to actually do it. And of course, I'm not paying anyone. I'm just doing it myself. But you gotta believe in the dream. Like one day, we're going to Mars, and this might be someone's first Martian job. All right, this already looks awful. So I guess if you do it like that. Okay. Then we're gonna try to slide in the other one here. And I did make a comment that the plastic here, this knee joint would deform as we tighten this knee bolt. And I just said that because, I just say a lot of things. Turns out it was true. Turns out it does deform. So who would have guessed? But yeah, this looks awful. Don't want to be doing this all the time. I wish this stack just would stay together. See, the assembly video is not as fun as the catting video. Here I have to actually use my hands and struggle in front of you guys. Oh man, who thought of these? Who thought of these? All right, when I put that in there, I don't even know if you can see these. It's all so small. I'm gonna put that in there. Don't have a lot of patience today. It's already Monday night. It's been a long day, but I still have my master order and I thought I must check it out. Oh my god. But maybe I'm changing my mind now. Which way does this even go? Yeah, this way, this way, this way, this way. Okay. Yeah, it's the kind of thing you want to assemble once and only once and never again. I wonder if there's a trick I'm missing, something obvious that I'm like, oh, should be doing that. I might just edit this out because this is so painful. Last video was me rambling for 2 hours. This video is just gonna be me suffering for 2 hours. Let's see what gets more views. Probably struggling, right? Small views. Irony. All right. Oh man, I don't know if that's gonna fit. It looks very tight. Oh. All right. So here we go. We're gonna try shimming this in there. Shimmy, shimmy. Yeah, this is not gonna work. No. Who thought of these? What a terrible design. I should have looked at the cat and be like, oh, that's gonna be painful to assemble. Huh, how could we do this better? I'm gonna pause the video for a bit here. I'm struggling way too much. This is why the person designing things should also be the person assembling things, so they get to experience the pain of their own choices. And I guess this was kind of my choice, but let's be real, I didn't think about these bearing things that closely. These open source project guys probably assembled these themselves and they were like, oh, you know what? I'm not gonna change it. These ends here, I will change these. I cannot let anyone else, any other human experience this, go through these. It would just be irresponsible of me. All right, this is the last try. This doesn't work. I'm redesigning this entire part. I don't care. And of course, we're gonna use the same bearings because we are like $100 into these things. All right, here we go. This is gonna explode. Yeah, it doesn't work. All right, guys, we're back to catting. I'm not doing these. All right, back to the computer. So, got back from Whole Foods and just realized my mic was muted the entire time. So, let me catch you up to speed real quick. And that's actually probably good. It was karma because I was being mean and said a bunch of mean things about bearings. But the biggest change that happened here was we changed the lower here. So you can see here, actually, yeah, you can see here, this is the old, what the old part used to look like. And it's like a small cutout, very boxy. And I made it a big U here. So this part kind of like opens up like that. And so the goal here was to get rid of two bearings that were in here. And so instead of two bearings, I grew these grooves here. And so you can kind of like open it and it's gonna interlock to the upper like that. And that was like a quick change. Basically, we only have to reprint one part. We get rid of the bearings, so that's good for the bomb. And I think we can even get rid of these bolts, this screw. I don't think we need that anymore. So I wasn't too sure on you know what's a good fit for this joint. So I just printed this real quick and it's actually done right now. So I'm gonna go try it. And while I was out in Whole Foods, actually, I also had another idea for, because like the other thing was removing this other bearing here. So I think I'm gonna replace that bearing with basically a kind of like a what is it called, like a clip ring, and like basically well, no, that's mixed panels. Basically like a retaining ring, sorry, like a retaining ring, like a snap-on retaining ring, but just reprinted. So I'm gonna replace that bearing that way, and that way I don't have to reprint the cam, which was like what I was afraid to do. And then the other thing was like when I was printing the lower again, I actually just playing with the support. And I went with these three kind of support, so very curious to see how it turned out. So I'm gonna go grab the parts right now. So this is a part. So So we have the old lower already assembled with some push rods, and then the new lower still with support. So one of the things I was saying on my video was that I kind of hate supports and I want to make sure we don't have any supports. But these 3 supports are actually, they seem to be much easier to remove. Still like not perfect, but yeah, definitely still not perfect actually. It doesn't want to come off. In general, just, we kind of want parts that are ready to go right out the printer, so no one has to spend time doing these, and you kind of don't need to have any skills, and basically anyone can just build their own robot. Or making robots can be fully automated and there's no post-processing or anything like that. Minimize assembly. But anyways, this is the final part. I just removed the supports, and it's what I was saying here. We made these U big and we gave them good nice fillets here, so it can bend. So if it worked, I should be able to just kind of jam this in there without making no changes to the upper. So I didn't reprint this part at all. So I'm just gonna bend it like that, and then you see it fits. Fits like that. And so there's no screw in there. We could put a screw, but I don't think we need a screw. Now I would make this a little, this whole joint a little tighter. There is some play. There is some play. You can see the gaps there were pretty big. I wasn't sure how much to make it, but and so our upper can deform a lot. You can go at an angle. Of course, we can compress this with a screw, and that will help. So maybe I do have to put the heated insert back in there, but we basically just eliminated 2 bearings right there. So I like that a lot. Yeah, we'll see how it tests. Obviously, we do have to run some tests here. But anyways, I think this is an improvement already. And so let's quickly just fix the quote unquote fix, eliminate the next bearing here. And replace with a snap-on ring. Also, on a previously, and this was not on any videos, I also printed servo horns, which actually I haven't even added to the assembly here, but these are just basically custom servo horns, and this yellow part and this white part are now one single part, which is this green rounded part here. And then I also simplified these other servo horn, which has multiple holes. Now it's very simple, basically as simple as you can get. So that was good. And anyways, let's just do some quick CAD here. This should take a minute. Basically, when I replace exactly the same bearing here, so we can just open that model and basically copy paste. We cannot open that model, but you know what? I'm just gonna take it from McMaster. So McMaster does have a drawing here. Should be this drawing here. All right, so let's just model that. I think we can add a part here. We'll name it retaining ring. Like I said, it's kind of Monday night right now. It's been a long day, so I'm gonna print these and call it a day there. Not gonna keep going with things. But if this turns all right, then the next step really would be to assemble a full leg and start coding the servos, which, yeah, I mean, that sounds like a good next step. And if that works, then I would order more servos. They come from China, so they'll take a while to get here, but I would get the full servos to build a full robot, basically. I think we're almost getting there, so anyways, This is basically the cam retaining ring. And obviously, well, okay, so we can give it some fillets here and there. Just something like that. And we do want this to basically be able to deform into place. And so we could do some math into, like, you know, what's the opening and how much it needs to deform, but I'm just gonna eye it out here. I'm gonna eye it out like this. Triangle. Again, because it's Monday night and I don't want to spend too much time on this today. Just want to be able to say that the leg is ready. So I'm going to give it 30 degrees. I'm going to get it 45 degrees just to be safe. And that's just random. And so I think if we cut this off here, and of course we could always, this is going to be a very simple part, so it's always, we can always come back to it if it's not enough, but this should be enough. Why is that not working? Remove, yes. No. Huh. Remove. Interesting. Okay. Yeah, so I don't see why this wouldn't work. Wait, what? Why is this not working? Oh, I see, okay. Okay. So I think something like that would work. Let's just add it to the assembly just to be super safe here. But let's see. Okay. Well. M is for mate. Cylindrical. Already getting the hang of on shape. Cylindrical, that's good. And then this is needs to be constrained axially somehow. Planar. This face. That face. That face. Guys, that face. Yes. Okay. Something obviously broke there, but that's fine. And bring the upper back. Oh, the upper here. Something like that. Yeah, something like that. Right. So the size seems fine. So I'm gonna go ahead and print it. This is probably gonna print in like 2 minutes. Prepare. Hmm, 8 minutes. All right. So I'll be back when that prints.
12 seconds later.
Party's ready. Let's take a look. Yeah, very bendy. This should work. So here's the old bearing, which we're replacing with this. You can already imagine which one's cheaper and which one's way easier to fabricate and get. And here's the cam. Obviously this bearing didn't fit in the cam, but you know, if Cat was right, we should be able to throw these in here. And you can see it fits perfectly. It's already in there. It's hard to see because everything's green. And then these should fit in here now, and that fit should be much better. And it is, there's zero play. And so now, the way this works is we should be able to put these in here, and everything should be perfect. I don't know if I have the right Allen key for that. Maybe not. So let's try it. I still want to add some heated inserts on the new lower leg, but let's just try it, just for the sake of it. And again, if this works, we're basically done with the cut for the leg. Then we just need to prove that you know, the servos will work, and if they do work, sorry, that wasn't. This is a wrong screw. Yeah, we just need to prove that the servos work, and if they do work, I'll go ahead and order 9 more servos for the other legs. Basically, when I put screws for these ones, for these other 4, not the central one. I kind of like don't want to screw it right now, just because I don't know what position the servo is on. So we would want it to be on a neutral position. So I'm gonna do the heated inserts first. Move all the hardware from the old lower to the new lower. And then power on the servos and make sure they're neutral, so we can screw down everything and just call it good. So gonna do that now. All right, so this is the first time the full leg is assembled. in one piece. So this is what it looked like, and we can see here the two different servos actuating. So when the lower goes up and down, sorry, when only the upper moves, you see the servo's horn is not moving. But then if we were to move the feet, pivoting around these axes, you can see only these will move and the upper will remain the same. So it should look just like a cat. So that's pretty cool. So like I said, next thing is actually connecting these two servos. I was supposed to do that before, but I feel lazy tonight, so I'll probably do it tomorrow. Initialize them, and then what I want to do is run some code to, basically fatigue test these, like maybe like go up and down 10,000 times just to see what fails. There's some joints all around that I don't feel super good about, mostly around the push rods here. Like I said, these screws are loaded in single shear, and the feet are not perfect, so everything's not perfectly aligned. This surface here and this surface here is actually not on the same plane. Also here, there's gaps. I don't know if you can see it, it's very small, but there's gaps. So all around, even though it does work and it looks good, and I'm sure to the untrained naked eye, it looks like a functional robot, there's all around, there's things that we can improve. Which we'll probably we're not gonna flash out on the first version, but if there's any like low hanging fruits, we will flesh it out. But yeah, so tomorrow, maybe, no promises. Tomorrow I'll probably code something on Arduino just to cycle these servos, and maybe have it running all night to see what explodes.
Tomorrow.
Hey guys, it's Tuesday night now, next day, and just got back from work. It's about 8 p.m. and I'm ready to do some work on the robot tonight again, just to keep momentum going. Pretty tired, but it's a reminder of where we are right now. Last time we put these together. So last night we did some quick redesign of a couple parts, the leg lower, and we removed all of the bearings in this design, so it's way easier to assemble. It's a cheaper BOM, less parts, and hopefully just as good. And we were gonna validate that last part, the just as good. And to do that, we were gonna run it, run the servos and cycle it about 10,000 times. So instead I'm gonna do that today. I kept thinking about, I basically 3D printed a kind of like a snap ring, like a retaining ring, which I think we don't need. We can modify that out on the cam part eventually. And the reason why I didn't end up doing it this last night, and I think probably sounded a little lazy, but actually it was kind of embarrassing. I was gonna hook this up to an Arduino Uno here, so I have a cheap knockoff Uno. And somehow I'm out of jumper cables. I only have female to female and male to female, but I needed male to male to connect the Uno to the servo wires. And somehow I'm out of it, which just goes to show that I'm rusty as a hardware engineer. So I had to call Jeff. So I called Jeff and I told him, hey Jeff, I need some of your finest jumper wires. And so, you know how Jeff is, he sent us some here. So I just picked this up, and so we should be good to go today. Just, I guess shout out to Jeff. Pretty amazing how Amazon can just ship stuff next day like that. I don't understand why would anyone sell the stock. I do own Amazon stock. I'm never gonna sell it. I don't care that the stock is up 1,000% over the last 10 years. It's probably gonna keep going up. Now they own a piece of Anthropic. Oh, who doesn't love that? Anyways, gonna do that now. Before doing that, actually, I'll show you one more thing. I said I was gonna initialize the encoders last night, but I kind of just wanted to assemble a whole leg, so I didn't do it. But let me show you what I mean by initializing encoders if you're not familiar with servos. So this is a servo motor, the type we're using right now. This is a very standard servo motor. So what's in here, it's basically a brushless DC motor, a gearbox, and an encoder. And so motors usually, if you think of a drone motor, they can rotate and rotate forever. But servos like these have a defined range of motion. And so if you see this horn here, that's as far back as it goes. And on the other side, this is as far as it goes. So that's 180 degrees basically of motion that we have. And so you want to make sure that your full leg range of motion is within those 180 degrees. And if you're assembling multiple legs like we are, you want to make sure that 0 degrees on this servo and on the other leg servos is the same position, no legs. So you want to initialize the servos when you're assembling. You want to assemble the horns all in the same position and the legs in the same position, which is something I didn't design for. So let's see how hard it is. And if not, we might do some CAD modifications for the next legs. Now, why do servos only have 180 degrees of rotation? There could be two reasons. One could be like they're using half gears in the gearbox here, so it can be such a tight package. But I suspect that's not true. I suspect probably the truth is that they're using potentiometers as encoders. And so potentiometers is basically a brush that wraps on a surface, and as it rotates, brushes in a different side of that surface and resistance changes. So using basically electricity, you measure a voltage difference as you rotate, and that's how you know where are you along that kind of like that path. And so it has to be a limited range, right? Because if you keep going, eventually you're out of your brush is out of the resistor thing, or it will reset to 0, and you need some logic. So this is why these cheap servos are constrained like that. At least that's how I understand it. Oh yeah, and then one last project update. After Jeff delivered the wires, I was feeling pretty excited. I'm actually pretty excited just to see the leg. And this is basically, we're in, what do you call this? This is day 3 of, tonight is gonna be day 3 of work. So we got these here pretty quickly, and I wanna keep momentum going. But I only order servos for one leg, and one leg is ready. And so these servos come from China. So I got into AliExpress and I said, ni hao, I need 9 more servos. So I ordered 9 more servos last night. And so they're also coming. AliExpress ships super fast to California somehow, which is like pretty cool. Not as fast as Jeff, but still pretty cool. So that's gonna come soon. And so the plan is like, tonight we test this, we cycle it, maybe we do some more cycling tomorrow, see if something breaks. If nothing breaks, we can start moving on to designing, first of all, the other side of the leg. So we gotta mirror these kind of like in this plane and generate like the mirror image. We gotta print those. And then the other thing I haven't done is the third servo, so the shoulder, to move it this way, to move the leg this way. Gotta start designing that. And once to start designing that, we need like a body for the dog, like a chassis, if you will, or just a body of the dog. And to design that, kind of like we need a rough idea of like the electronics, what's gonna go inside, batteries, compute, the jets and nano and stuff like that, and what kind of stuff we need to sort of know how much room we need, how to package things. I put 0 thought on that, but I have a friend helping out, so maybe I'll invite him to one of these videos and we can talk about it all together. He's really good. He works in robotics. I have a couple of friends who are gonna help. Both of them work in robotics. I'm like the outlier SaaS founder here. But yeah, anyways, enough talking. I'm gonna get started. One more thing I wanted to say was shout out to Bamboo. This like is green just because that's the color of the free filament from Bamboo that they included. And I'm still running on free filament. I haven't had to actually use the filament I bought, so that's pretty cool. Well, probably should share my email here. I wanted to, what else? Talk about one more thing. I guess quick shout out here, but I posted the last video on Hacker News, and someone asked, how do you juggle doing something like this plus building your own company? Because they saw I have a YC, I'm on YC and building a startup. And I was saying I don't see it as juggling along with building a company, but rather a creative outlet that helps keep burnout at bay. So even in days today, like today was a pretty long day at my quote unquote day job. And SAS, SAS, especially with someone with a hardware background, I think can be very, people say brain rot. That's one way of saying it. It's not as exciting. You're just staring at a screen all day. The lifestyle is very, I would say, static, which I don't love that part. And that's why I like actually doing stuff with my hands from time to time. And that's why this gets me excited. And this is part of why I do it. You shouldn't see it as a distraction. You should see it as this helps me stay motivated and get that extra energy that I have, put it out into something useful in a way. When SAS is not a good outlet for that. Yeah. Yeah. Pretty cool. Pretty cool to see people leaving feedback, even if it's negative. I still appreciate it. It means they took the time to at least think of something to say, which is pretty cool. Here's a retaining ring we made yesterday on the fly. Sure. Alright, and let's open this package from Jeff. And as expected, it's a box with jumper cables, jumper wires. Alright. It's a lot of packaging for something so simple. Yeah. Oh my god. Alright. I don't know if all these packaging is required, but yeah, we should be good to go. Where's that Arduino? Where's that Uno? All right, here's my Uno. I am using a Mac, so I think we're gonna probably spend some time troubleshooting that today. Usually, Uno doesn't play super nice with Macs, in my experience. Here's the Uno IDE. If you don't know Arduinos, that probably means you've never worked with hardware or you're less than 20 years old. You're 20 years old or younger. These are pretty old, kind of like chips, microcontrollers that you can basically program using the Arduino language, which is basically C. There's a lot of libraries, and you can connect all kinds of things. And these boards are pretty cool. They have built-in power supplies, different voltages. You have PWM. They support also analog, and there's also all kinds of shields that you can use to make it do fun things, like have Bluetooth, wireless, or there's shields for servos specifically. And a shield is just basically another PCB that sits on top and has like its own ICs and inputs outputs. So these are pretty useful things. I guess like an alternative to these would be maybe like a Raspberry Pi, but that's a little more complicated to set up. So Arduinos are neat, and I always keep one just when hacking things like these. It's not like we're going to actually use a Uno on the final on our final product, on the final robot. Not a product. We're probably not selling these. I haven't figured out a good way to monetize robots. So I'm on a laptop here, so I'm out of USB ports, thank you Apple. So I'm gonna disconnect a couple things. So my mouse, I'm just gonna use the trackpad here. Hopefully you can still hear me. So we're connecting here for the first time the Uno here. We should see some lights. And I'm a bit rusty on my C, so I'm just going to explain to ChatGPT what we're doing and ask it to generate code, and I think that will work. So we should see lights up. That's good. Allow accessor to connect. That is also good. And we basically have to do two things. First, we need wiring, so the electrics, and then software. I don't know which order, whichever order you're comfortable. I'm gonna run here a very basic script. So there's a bunch of sample scripts, and there's one called Blink. So this one's blink. So you can upload blink just to, you know, make sure everything's working fine. And so doing just that. And so first you gotta, before uploading, you have to verify. And once, you know, verify, I don't know if verify is the same as compiling, but okay, so it verified, and then you can upload it. You gotta select the right serial port, obviously Arduino Uno here, upload, and ideally it will successfully upload here, and it looks like it successfully has uploaded. And now you can see this slide here. Can you see it actually? Can you see it? Yeah, where my finger is, it's blinking. So this code is called blink, it blinks. So we've successfully validated the connection from the Mac to Arduino. So good job, guys, we're almost there. I did have a conversation with ChatGPT, I think, last night, or maybe not. Maybe this was a dream. Okay, new chat. No, control to servos. Yeah, so I told ChatGPT I have an Arduino Uno. I control 2 servos with it. They use PWM and should be able to run on 5B. I don't remember if I said this yesterday, but actually, yeah. So Arduino's, you know, it's right now it's being powered by my computer, but I also have I have a 12V barrel to connect to the wall outlet. But even then, I think they only provide like 5B and maybe 1A. So we're gonna be power limited when running our servos. So that means we're gonna have less torque and less maximum speed, which means, you know, maybe wear and tear won't be as bad on the joints. But this is kind of like a rough test, so we'll have to do. So let's see what Arduino, let's see what ChatGPT said, because that's our setup. That's very simple. Yeah, you can tell control the servos in Uno. The Uno has 6, yes. Quick setup, connect the servos. Okay. So let's do the electrical right now. So let me find the right cables. Like I said, we needed male to male jumper wires. I'm a mechanical engineer, guys, by the way. So let me know if you can tell this is one of my weaknesses. All right, so we're gonna try to keep it civilized here. So we're gonna do black wires for ground. Black for ground, red for 5B. I was gonna say voltage, and I like to keep my PWM wires blue and purple. We're gonna do blue and purple, and so I'll show you guys in a bit what's going on here. It's on the desk here, so hard to show, but let's see what Arduino says. Signal pins of the servos to any of the 2 PWM in the Arduinos, pin 9 and 10, right? So we're gonna grab our, remember I said I like my PWMs to be blue and purple, and we're gonna put this in pin 9 and 10. And so Arduino actually labels all the pins with numbers. This is the cheapest one, this is a knockoff, this is not the official Arduino Uno, and even this one has labels. This is like maybe like $10 or less on Amazon. So we're looking for 9 and 10. So down here, 9 and 10, and you can see here it says digital PWM. So 9 going blue and purple going 10. And these jumper cables from Jeff fit perfectly. Thank you, Jeff. And power and ground to the Arduino servos. So ground, you just look for ground. It obviously says GND. That's how Arduino signals ground. Yeah, there's a couple grounds. The one thing is that there's not a couple of 5Bs. There's only one 5B labeled. But I'll show you a little hack here. So actually there's an extra 5B on the Arduino. It's just not labeled, but it's on one of the things that the shield uses. So this is Arduino Uno schematic. So down here, I think one of these is 5B. Reset. Okay, well I thought, oh yeah, 5B right here. So we have one 5B labeled. It says 5B on the wall. And then the other 5B we're actually gonna take from this pin down here. The only trick here is that that one is a female to male. It's not male to male. So we do need a different kind of wire, but it doesn't matter because Jeff hooked us up with every single kind of wire possible. Once again, thank you, Jeff. Video not sponsored. I do hold Amazon stock. All right, so all the wires on the Arduino side are set. And now I'm gonna connect just one servo for now, just to see how it runs. Let's not get crazy and connect the entire leg. We still need to initialize it anyways. This is a servo wire, so you'll notice 3 wires. Obviously we have ground, power, and PWM. Ground being brown, power being red, and PWM being orange. So my ground is black, goes to their brown. My power is red, goes to their red. And then my PWM is blue, goes to their orange. And so connected like that, we should be good to go here on the hardware side of things. And so now we're gonna follow the step number 2, install the servo library. So on Arduino, it's not as easy, it's not like a terminal, or it's not like Python where you can just pip install some libraries. But you can, there's a library manager and you can, install libraries here. So servo, I think that's what ChatGPT wants. And here's the code, so we can just copy the code. And then it says we can just upload the code. Honestly, I know people say, oh, don't upload code from ChatGPT, but I just do it. So this is what it is doing. Let's just read it before, so we understand what's going on. Always read the code before you upload it. This is particularly true. Well, this is always true for anything. Okay, so it's setting the servo to 0 degrees, waiting for a second, and then setting it to 180. So I was saying these servos have at 180 degrees of motion. So it's ChatGPT assumed the same, so made a right assumption. I'm uploading the code, and as soon as it uploads, it's already moving. So you can see it moving. So that's cool. So code works. This is super straightforward. Now, what I want to do, the way we want to initialize it, I'm just going to leave this running in the background. Now, let's think of how to initialize the servos, right? So we have the code working, and it was pretty straightforward. We have 2 servos. So one controls the upper here, and the upper, this is the top range of the upper, right? So the servo could be 0 here. And then this is the bottom range of the upper. It cannot go beyond this position because we are already cutting here, which is not a good hard stop, but it is what we have right now. And so our range, it's realistically our range for this particular servo, it's probably in the range of 80 degrees. So at 0, we want to set the servo at 0 and then put this down all these 4 screws. So that's for the top one. Now for this one here, the one that controls the lower, so this guy here. Sorry, I'm gonna constrain it. This guy here, I'm doing a terrible job of constraining it. But basically this servo horn here, it basically goes from here. It cannot move past this position because we have collision here. And then on the other end, it goes here. So what would we call that? Again, it's less than 90 degrees. It might be just 90 degrees actually. But okay, so why can it move beyond here? Because we have collision. So I like the collision points as good points to start at 0. And so what I'm gonna do is I'm gonna remove all these screws. Oh no, actually I'm gonna write code to set the servos at 0. I'm gonna make sure both servos are at 0. No, actually, before. I'm gonna remove all the screws to the servos, connect the servos to Arduino, set them at 0, and then we're gonna nail down the screws again. And our zeros will be, like I said, for this one here, this is 0 when the leg is folded like this, and for this one here, this is 0 when this is touching. So let's do that right now. I don't know how you can actually get a better sense of what's going on here. Maybe I'm moving back to the tripod or something. Yeah, I'm gonna bring the tripod. I'll BRB, guys. Ooh, this takes forever. Removing its bolts. I do have an electric screwdriver, but I prefer to do it manually, especially with these screws that go into plastic, as you don't want to strip the plastic. If that happens, we would have to reprint the horns, which is not a big deal. It's like 10 minutes that I don't necessarily have right now. Oh, okay, so turns out those were the wrong screws to remove. And the reason why these are the wrong screws to remove is because here we have only 4 screws, and so our control to change the angle here, it's very much limited versus doing it at the servo horn. So the servo horn, I don't know if you guys remember, the servo horn has a bunch of teeth. It's basically a pinion, and those teeth are very small, so we can really control the angle there much better. So I want to put these back on. And remove the center screw. I don't know, if you've been following along, it might make sense what I mean by the center screw. There's basically a screw in here. It's just hard to see it, but it's in there. By the way, I was thinking, like, I don't know if I should open source this leg already. We're gonna open source everything eventually, but I don't know if anyone's interested in just the leg. I cannot tell if this is the right Allen key. I feel like no torque comes through. I kind of hate when you need a bunch of different Allen keys just for the same assembly. Alright, I have options here. You must see this one, I can't tell. You guys want to check? Let's check what CAT says. CAT says it should be an M3, and this is M3. So. Electric screwdriver. Okay, so that's off now. And so now it's only friction holding the horns onto the servo pinions, and we should be able to pop those right out. So that was off, and you can actually see the you won't be able to see this, but the servo pinion actually left marks on the horn already. So it happens almost instantaneously, as the plastic is much softer than the steel. Alright, so I modified the code so the servos go to 0 degrees and they don't cycle to 180. So now both of these servos are at 0 degrees. And I'm going to keep them there until we can figure out what's the correct position to put the horns in. So let me reassemble these horns first, the upper. And I'll do upper first and then lower. Upper is easier, I think. And so it doesn't really matter what position the servo horn is in respect to the upper, since, like I said, most of the angle control is going to come from the servo pinion on the horn side of things. So this can just be any orientation here. Alright, so when this upper maxes out, we said it would look something like this. Except I don't think this fully constrains it in rotation. Yeah, so that's another issue. It's not fully constrained like this. like it's constrained. Yeah, it's not constrained. So maybe need to spend more time thinking about that. The other thing is that I put the horn, the servo horn, before the retaining ring, so now I have to disassemble this again for the third time tonight. But yeah, I think it's gonna be an issue since we don't have any features that constrain the leg with respect to the servos. So it's kind of just floating there. I could check CAD, but I think for tonight it's not a big deal. We're just trying to start cycling the leg. Alright, so those come off. Then the upper fits through the cam and the retaining ring, and now these can actually get screwed. Just like that. So we're basically sandwiching the retaining ring, which constrains the whole assembly axially. And so when it's in, so we're doing this again, much easier with an electric screwdriver. Even though we might be wearing out the threaded plastic inserts here. Alright, now I'm just gonna kind of eye it out. I didn't want to say eye it out, but I'm just gonna eye it out. I don't know how. Yeah, I'm not sure if there's a better way. Just gonna eye it out. I mean, when the servo box, let's just say this face should be parallel to the ground, and so when the leg is parallel to the ground, I'm assuming something like I'm looking at the feet here. Something like that, maybe. This is as parallel to the ground as it gets, or maybe something like that. Trying to figure out how far the feet goes. Something like that. If the feet goes as far down as there, so the leg can be, I think basically here. So I'm gonna push this in, and now that that's pushed in, both are pushed in, both at zero pushed in, we can start assembling these again. So that's actually too long for my electric screwdriver, so I'm gonna have to finish it manually, but that's fine. These are like the cheapest Allen keys, so the fit is terrible. Anyways, now our servos, now our leg is properly assembled, and our servos should be initialized correctly. So now we can go back to code. Actually, we can first of all connect all the servos here, finish the wiring. I don't know how much current these servos pull. There is a chance that we'll either trip the Arduino or my Mac's port, since a laptop doesn't put out that much current. But anyways, this is initialized, and let's write some code. So first of all, I don't know which one's servo 1 and which one's servo 2. So we're gonna cycle 1 to 30 and 1 to 10. So I'm verifying this code, uploading it. Whoa. Okay. I don't know why it's not cycling, and it's also getting pretty hot, so I suspect it's an overcurrent situation. So let me go find a 12-beat barrel for the Arduino. Okay, so I disconnected one of the servos because I do think it's pulling too much current for the Arduino, but I also think that it's not respecting the angles on the code, and it's actually trying to cycle past the stops here, the hard stops, and that's what's triggering a current spike, and that's why the Arduino is it's flipping. The reason why I think that it's because the Arduino keeps going offline on the computer, even though all the lights are still blinking and stuff, but that seems wrong. So let's try that again. So I basically reduced the range of motion here to 1 degree, and it's still, I have it at 1 degree and it still does the full range of motion. It still means something's wrong. Okay, now it's doing much smaller movements. Maybe I believe that's 1 degree. Okay, so if that's 1 degree, let's see 10 degrees. So 1 degree, you can't even see it. So next I'm going to do 10 degrees, let's see 10 degrees. That is not 10 degrees. This could be 10 degrees. Very jerky. And the reason why it does full range of motion sometimes is, I suspect the servo library initializes servos by doing something like that. I need to look into that, but I think now this looks like 10 degrees to me. This is 0 for sure, and this could be 10. So I'm gonna take it up to 70 degrees, which is what I had it out to be. And I have that 12B connected to the power outlet, so we should have more current. So I'm uploading the code for 70 degrees. It's cycling here. I don't know why it does that. And now it's giving us 70 degrees. So that's much closer to what I expected, although we still have some range left here. So I'm going to go up to 85. I also have no stop, so it's just going to keep cycling like that. We're basically maxed out, but we still have some, actually I guess here, we're basically at maxed out. So that's our range from 0 to 85. 85 degrees on the servo. Let me see if I can find anything on the servo library. Okay, this guy's gonna kill himself. The servo library. Okay, so the servo doesn't initialize it like that, which is interesting. I need to buy clamps or something for these. Yeah, I don't think I have clamps. So. Let me look for clamps. All right, so I don't really have clamps here, so I'm just gonna hold it with my hand, and I'll try to get clamps tomorrow. So, because if we're gonna cycle it to 10,000, we actually need clamps. But okay, these servos looking good. Let's try the other servo. So I'm gonna, whoa, that almost touched my face. I'm gonna focus on the servo, on the other servo now. And we calculated this to be basically, I think, around 90 degrees, but I'm gonna go easy on it. I'm gonna start with 50 degrees. Now when you're wiring this Arduino and stuff, any ground will do with any power, because they all ground to the same thing, which is the copper layer in the PCB. We're hitting that safety stuff here. Which should not happen in theory, so. I'm gonna start with a smaller angle of 10 degrees. And if that doesn't do it, I think I must have initialized the servo wrong for that to be happening. So here we go again. So it's still trying to push this way. Even though I thought 0 for this guy would push in that way, but because this guy is flipped, it means I initialized it wrong. So that sucks, but that's fine. It's an easy fix. I just need to basically remove the servo horn again for the millionth time. Before I do that, let's make sure it's at 0. Actually, no. Let's make sure it's at. I actually first remove the leg, and then let's make sure it's not at 0 but at 180. Do you guys understand why? It's because like this is mirrored. So what's 0 for here, this guy should be 180 for this guy. Which maybe if we had gone slower and just think things through, it would have been obvious. But it's 9 p.m. so just actually trying to get it done. You can't see a thing, I just realized. Now you can see. All right. This electric screwdriver is great, by the way. Highly recommend. So now we gotta pop this guy off. It's a bit tight in there. A knife is great for this. Okay, comes right off. Now that that's off, we can use code to initialize that guy to 180 degrees. And the other one starts from 0. This one's gonna start from 180. And we're gonna upload this code, verify it, upload it. Now it's at 180, and it's staying at 180, so that's good. So this guy moves like this. All right, so this time we can cycle this guy from, I estimated about 90 degrees, 180 minus 90, obviously it's 90, but I'm gonna go easy on it and I'm gonna cycle it 30 degrees at a time first. Verify, upload, here we go. We're actually hitting the stop here. And actually when it's hitting, it's actually already denting the plastic, which is interesting. But okay, let's try to find the full envelope here. So I said 90 degrees for this one. I'm gonna try 90. So 180 to 90 for the second servo. Let's see it. We still have a little bit left here, but it is very close. So I'm gonna call it good because I don't think we're gonna need more of that than that range. All right, 95. Let's try 95. Let's push the limits here. Verifying uploading. Yeah, that's closer. All right, so now we have two servos that should be, so I'm gonna connect the second servo, and with the DC source on, I think we can handle both, since they're not hitting the stops anymore. Not hitting stops and not causing any current spikes. Okay. That looked wrong to me. I don't know. Hitting a limit here. You can see that, you can hear the servos struggling. All right, so I'm gonna disconnect it for a second. Let's think this through. So when these maxes out here, this guy can push all the way here, but it cannot come all the way here. Well, it actually can. The issue is actually when this guy is like this, and this guy, and then the other guy seems to be wanting to also fully extend. And you can see, basically it hits here, but it hits it so hard that it actually overlaps. And the plastic goes on top of the cam, this push rod goes on top of the cam, and then it pushes here, second safety stop. And then you can hear the servo trying to keep pushing through. So, trying to think what's the solution. Well, a solution, it might be, a temporary solution might be to reduce the range of the second one. So instead of starting at 180, we'll start at 170. So I'm gonna take 10 and then see if that does anything. So verifying uploading. Let's give that a try. Should be verified, should be uploaded. When I first connect this small servo, it's much gentler. Okay, all right. So you can see here, oh, that's bad. Whoa. Trying to like picture when do things go wrong? Okay. All right, I'm just hurting the leg here. Let me use big brain, think hard. The two boundary conditions are this guy here, and then when this guy is here, this guy can go this way. So this is the 180 side, but it can't. Oh, and it can probably. So this side is fine. All right. The other boundary condition for this guy is somewhere here. And when we're here, this guy basically can't do a thing, because if this was to move anywhere, well, that would also move the, right? It would also move, I think. So when the upper is bottom out here, the other guy can't do a thing. Which is interesting. So yeah, so I need to think this through a little bit more. But for tonight, I'm gonna call it a night. We have the leg running. We just need a better kinematics equation. But it's 9 p.m. so it's been an hour of trying to figure this out, and I think it's in working condition now. So by tomorrow, I'll have an equation for these, so we can cycle these repeatedly. Again, the next goal is to cycle these 10,000 times and see what breaks. So I'm gonna call it a night here.
Tomorrow.
Hey guys, it is now Wednesday. Sorry for the dishwasher. So today I think it's gonna be, this is the last time I'm gonna film for part 2 of this series. And so, well, first of all, one update is I got some clamps from Jeff, so now we can clamp it to the desk, so it's not like just me holding it on a hand. And just to give you an update of what happened last night, basically, we finally got these moving with an Arduino, so the servos are rotating, at least 2 of them. But I totally failed to account for the fact that there's a lot of, basically, I mapped out the ranges where the servos can rotate without clashing anything for each specific servo. But there's a bunch of combinations of different angles on the 2 servos that will result in collisions. So what I need to do is to basically come up with some operating envelopes for both servos, and so the leg is never clashing. So there's a few ways of doing that, and I think the more educated way of doing this is through something called reverse kinematics equations, which you basically come up with a set of equations that describe the motion of these linkages, and from there you can control you can control what angles the servos can go, and at what angle the other servo can be in based on servo number 1. So that's one way of doing it, and if I'm honest with you, that is kind of like a lot of math, and haven't done that since school. So I was like thinking like maybe not that. The other thing is like I actually, since we're building up from an open source design, I actually don't have these mapped out as linkages, so I have to rebuild that. So I kind of like don't want to do that. So instead I had 2 other ideas, and we're gonna do one of them today, and I think that'll be enough. So one thing we could do is, like I said, I know the safe range of motions for both servos on their own. So let me just demonstrate that here. For example, I know these servo on the upper can basically sweep, I think it's 85 degrees safely without hitting its stops. So that's good. So we could like stop every like 5 degrees and then figure out, okay, how much can the other servo rotate without clashing anything. So that's one way of doing it, except that's gonna take some time, right? It's like 17 different angles, and for each angle, find the 2 positions of the other servo, and then kind of create this lookup table, which we can probably reference in the Arduino code as an array or something. So we could do that. I think that's gonna take like probably over an hour. The other thing that we can do is we could do something like that in CAD, right? So we have the 3D CAD of this robot, and we can just do this same approach, basically model it and like rotate it and figure out what angles the other servo can go. And I don't think this is one-to-one to CAD just because compliance and the way things were assembled, but I think it's close enough, and with some safety factors here, we can get away with it. So I think we're gonna do that. By the way, I just wanted to demonstrate. So yeah, this jig will make it very easy to cycle through. It can move much faster than this. Right now we have a 1 second delay, 1 second delay every time it reaches a position. Obviously, it can move much faster than this. The other thing is like I have put zero thought as into what like a proper walking motion looks like. So maybe like on the next part of this series, we look into how dogs walk, and we kind of like try to mimic it with this leg. Maybe that's a good approach. For now, what we're actually trying to do is to load test these, cycle test it. So I care more about like the maximum envelope movement than a movement that actually walks. Oh wait, I'm gonna stop cycling that. All right, let me cycle the other one. Just to show, on their own, they both look, pretty cool. It's the issues when you combine them that, you reach all kinds of problematic situations. The other thing that I wanted to talk about, and this is more like towards the I don't know, craftsmanship and structural optimization stuff, but there's a lot of fits in this leg that can still be further improved, and actually this leg doesn't feel super sturdy. There's gaps in between parts that shouldn't be there. The cam actually moves a ton, and look at this, like, of course I'm kind of nitpicking because like it will work. It's just that, you know, we can build something more robust. We can build something better. Now, before we get to work on the CAD, I've started reading this book, The 38 Letters from J.D. Rockefeller to his son. So these are letters from Rockefeller to his son, as the title describes, and they're unedited, so they're just the raw letters. I just started reading this book. Rockefeller was, of course, one of the, probably like the richest person in history, I think. He created Standard Oil, which was split into different companies by Teddy Roosevelt, President Roosevelt. But anyways, he has this quote on letter number 3. The greatest reward for our hard work is not what we get, but what we will become. So, and I think a lot of people say, you know, it's not about the destination, it's about the journey. It's not about what the hard work gets you, it's about who the hard work allows you to become, kind of thing. And I think a lot about it when, you know, starting new projects and even building startups. I was just thinking about it, about that Hacker News comment on like, oh, how do you balance building these and building a startup? And to me, it all comes down to like making sure you're enjoying the journey and growing as a person. So I don't know, I thought that quote was cool. Anyways, let's get to work. All right. So picking up exactly from where we left here. So yeah, we had our Arduino schematics. This is all figured out now. The other thing I need to do is to create a GitHub repo to house this Arduino code, which is very simple. I keep thinking of if it's ready to be open source, yes or no. I still think it can be better. And I also don't know how much utility just a leg on its own will have. Something that I've been thinking about though, it's like this design, one of the strengths of this design is how the servos are packaged, because let's open the CAD here, but because it's kind of slow. Okay, a bunch of parts are hidden, I think. Let me just make my point. All right, because the servos are all basically in a single region of the robot, and so really, if you wanted to use the same leg with different servos, you don't have to modify the leg whatsoever. You might have to enlarge or change the size of this box, but that's about it, right? Because basically all the servo horns should fit on any servo. I think it's a pretty standard pinion size, yeah. That's true for both of the servo linkages here. So that's a pretty neat design. Of course, this might not hold true as we start to work towards the body and the chassis, which hopefully we can get started this weekend. And that will be more involved, but yeah. Anyway, so the plan for today is to, okay, servo is doing bad things. Plan for today, so yeah, that's kind of like how it looks like in real life. We need to create a lookup table with angles where the servos are happy with each other. Actually, do I have a servo in Chartic? Let's see here, angles. And so we're gonna have servo 1 and servo 2 min, servo 2 max. And so servo 1 is going to be the servo in the upper, so the one that moves this guy here, just because one, you know, from the top, and then we're going to move down, and this is the main servo in a way anyways. So and so maybe we'll start with, you know, degrees. Yeah, the position in degrees. And so servo 1 will start at 0, 5, and like, let's check. The code says servo 1 can go from 0. In the code, servo 1 is servo 2, by the way. So very confusing. I'll fix that. But it can go from 0 to 85. And so, you know, we'll take 10 degree increments here and go to 85. And for each angle, we're going to figure out where can servo 2 go. So the first thing we need to do is to figure out where servo 1's 0 degree is at. I'm just checking. I'm out of frame here, but I'm just checking the jig, the leg in real life, just to see roughly what that looks like. And I'm gonna try to get an idea for it in CAD. All right, so basically servo 1's 0 degree is when these two elements collide. So somewhere around, okay, well, if you could stop moving, guy. I'm gonna fix servo 2's horn for now, but basically where these two guys collide, somewhere around here is 0 degrees for servo 1. And so I think, which is interesting because, no, it's not, no collision. Yeah, so that's like servo 1 0 degree. And so now what we need is a sketch. So from here, I'm gonna sketch all the elements here. Or I'm gonna attempt to sketch the elements. And so having never done this before in Onshape, I'm just gonna like do what I would do, or try to do what I would do in SolidWorks or in CATIA. And by the way, so Onshape is really growing on me. So I'm gonna create a new part. I'm gonna name it skeleton. And on the front plane, I'm gonna make a some sort of sketch here. This is a placeholder just so I can position it correctly. And we're gonna go back to the assembly, and I'm gonna try to insert this skeleton, which is very interesting because it looks like it worked. It looks like you can import a sketch, and you can rotate it even. Now I do need to sort of constrain this sketch to something. And I'm gonna try to make that something, or well, I don't even know what that something could be, because I think mates are based on features. I'm just trying a bunch of things, see what works. We'll see. Okay. I wonder if I can modify this sketch. I can modify the sketch. All right, perfect. So I'm gonna delete this, and basically what I'm trying to do here, what I'm doing here is recreating the leg. Yeah, recreating the leg. So there's one element there. There's a horn here, and all these guys basically move to get there. So let's see if this makes sense. Let's see if this works. So that's a body here, and I don't know if it makes. I don't think we need to model the leg all the way down, but we might. It might be helpful. Okay, so I wonder if I can make this concentric to this. Doesn't appear to be working. It appears to break things. But let's keep going. Okay, it's not exactly. Oh, it was because of perspective. Let's keep going. This seems to be working. Okay. Okay. All right. And okay. So this is basically the leg here. I'm gonna remove these. We don't need these. We actually don't need this at all, I think. So this is basically the leg. Of course, it's fully constrained to the parts, so none of it can move. That's why these lines are black here. What we want to do is recreate these without having to reference parts of the body, and so instead we're going to reference angles and lengths. And we also need to map out the stops so we know where things clash. Yeah, so the way we do that, again, never done this before, but you start removing the mates one by one, and then you pick something to reference everything to. Ideally something, you know, kind of like that makes sense. So I think this pivot point makes sense. And so now this servo horn is fully constrained. Oh my God! Without relying on the assembly. So if that makes sense. So we're just gonna keep doing that for everything. And what's cool is that once we have these for the part, basically we're set. We can reuse these for all future kinematic needs. Now you can see here that I defined the servo length, and that's not enough to fully constrain it. We also need an angle. And so this is servo 2, if you remember. So servo 2 starts at 180, and that's, yeah, so, well, I don't know, like the angle with respect to what, right? So it's like, I think we're gonna make a construction line here, and we're gonna measure this angle. And so we're gonna have it at that, whatever that is right now, just to not mess with things. And now same thing here, remove these. All we need here is the length. Geometry will fully constrain this guy. I'm gonna move towards here. Don't need that. These distances are funky, but it doesn't matter. It really doesn't matter. Because this is a solid, so whatever it is, you know, that's fine. Whoop, I need to stop doing that. Hopefully what I'm doing here makes sense for you guys. It really isn't complicated at all. It's just straightforward stuff. And really, like I said, I'm going through all these trouble just because I didn't want to do some math. But maybe you guys want to do math, you know, it's like, math is good, guys. Math is good, don't be lazy. I'm being very lazy. Shouldn't be lazy. All right. So we have our angles here. It's kind of weird that that one is a weird one, but okay. And why is this not fully constrained? We're missing one angle, and that's the one of the upper servo 1. So I'm gonna do the same thing here, construction line. I wish SolidWorks has, or NCATIA has a way of making infinite length lines. I haven't found that yet in yeah, infinity in on Onshape, but yeah, this should be ideally an infinity line, and so we're defining the angle to what's not a real line, it's just infinity line. Now that we have these, and like I said, this is supposed to be 0. It doesn't say 0, it says 1 point, you know, whatever. So we're gonna take this as our 0, and we're gonna go from there. So the next one is gonna be these plus these. Am I messing this up? Oh, wait, why? Oh, it's at 6. I'm a little blind. Oh, no. Oh, I see the issue. Just doing some Excel math here, and so our 0 is actually 1.75, so I'm gonna add, you know, that 1.75 to all angles here, but it's the same angle for servo 1 in degrees. It's just a small correction factor. All right, so the next angle we will have is, you know, 6, and what I want to show to you guys is that everything is gonna move. So 6, and that's where the leg should be,
And now the next step is to figure out, okay, what are the set of angles here that work for this guy? So now we're ready to start. We just need to cycle through it. So let's do that. So let's go back to what we think is close enough to a 0. And like I said, there is going to be some safety factors here, but okay, this is what we call 0, right? This is what I call 0. And for 0, so in real life, our servo 2 can actually cycle its full motion. So servo 2's motion should be 180. Okay, 180 breaks the thing. Let's see. Oh, let's make this driven. And let's see what driven means. It's not defined. It's gonna kind of like measure it live, but it's not defined. So it gives me the ability to move it myself. And let's see what kind of angles we can go to. Oh, okay. I think I made a mistake here. So I'm thinking. No, it's fine. So on servo, for the servo 2, which is servo 1 on Arduino, our range was 170 to 85. Now the question is 170 from where, right? So 170, so this is 145, and it's looking not happy there. Plus, I'm pretty sure we're colliding somewhere. Unclear where, but so I think we're measuring the angle from the wrong spot. Let me again just check the actual leg in real life. Okay. So it's kind of like from here to like here, something like that, 52. So the range we're looking for is 170 to 85, 180 to minus 52. So I think we're measuring wrong. And so instead from here and here, we should be measuring from here perhaps. Not that that makes a huge difference. It didn't make a huge difference. Let's try 140. And like I said, I'm looking for, looks like 170 should work, but well, okay. Well, let me see. It looks like in real life if that 170 works. I'm a very practical person. Of course, there's probably smarter ways to approach this, but well, okay. So I'm just looking at my leg in real life, and that looks about right to me. So I think we have the right angle now. So I want to make this slightly smaller, bring that table here, and so for our 0, we're gonna say, the minimum, okay, maximums, just going with largest number, 170, and then on the other side, we're gonna say I think 85 is supposed to work, and 85 is working. It does look like. We should be able to go all the way down to 49. Something must be wrong. Yeah, I think I'm still not measuring this correct. I think instead of here, actually, where we should be measuring from is here. Let me just look at my leg one more time. Yeah. Oh, wait a second. 170. Man, that doesn't really make a ton of sense. 170, 85. I will show you guys if this is useful, but I'm just trying to think here. Just seems like it's measuring from some random angle. There's another way of doing this, which is instead of which would be to put a correction factor on these ones as well. Does that make sense? So yeah, I think that makes sense. So what I call 170 looks kind of like this. And it's actually 42. So we're gonna have a correction here as well. Correction. And that's kind of like just stating a reference angle. And so our it's gonna be 42.2. And so and so 170 minus 42.2 should be 127. No. No, our correction angle should be, we can do these, and so it's like one, no. We could do these, and so correction factor could be 42.2 minus 170, and so we know that this is actually, sorry, it should be 170 from 2, and so we know that the actual angle in code should be these 170, and then on the other angle, you know, at the other extreme, where I don't know where it actually collides. Maybe it doesn't collide anywhere, but by code we know that's 85. So let me do some math. No, that's not the math I'm doing. Let me do some math here. Man, it's tricky. Looking for 85 here. I guess if we say that 42.2 is 170, then we just want these plus the difference between 170 and 85 is 85. So these plus 85 would put us, so 42.2 plus 85, that's the angle, put us here. That makes a lot of sense. I don't see the angle. 127. Okay. So it's basically cat. Okay, and so sorry guys, I'm still wrapping my head around these. So we have my Arduino angles here, and on cat, so on cat that's the equivalent of 85 is 127 42.2, and the equivalent of the other one is 42.2. Does that make sense? And so cat 1, cat 2. Sorry, I'm getting quiet because I'm thinking hard. All right, so the maximum is 170, which on cat is 42.2. So to translate that, basically, the correction factor is that. And the correction factor for this one is this one. Now, shouldn't they have both the same correction factor? I do agree with that statement. Okay, so this one seems fine. Right? If it's 42.8 on cat, fine. That one seems fine. That's the maximum, equal to 170 in code. And then the minimum, and just judging by how much angle it needs to change, is 42.8 plus 85, which is 127.8, which is what we have here. It's equal to 85, and the correction factor is different. I think we can roll with a different correction factor. So basically, what we use the correction factor is to solve for the Arduino angle, and so going forward, we would just use the same correction factor for everything here. And so, okay, yeah, we can make that work. Same for here. Yes, and instead, well, I guess we're adding on this one. Just different reference angles, I guess, which is, it's probably fine. Okay. All right, cool. Totally makes sense, right, guys? All right, so let's keep going. So now let's change the angle here to 6.18. By the way, if I'm doing something completely wrong here, it's gonna be very obvious pretty soon. It's just gonna be catastrophic. As in, like, we're gonna run it and everything's gonna crash. So I need to do one more thing. So let's put this back to, it's not entirely clear to me where do these clash, right? So this angle here, 27 point, that's the minimum. So it's very useful to have a graphical indication of at what angle these things will crash. But we don't have that right now, so anyways, where's my angle? Did I delete it? This guy here, 6.18. Okay, so for these here, it looks like we can do at least, I'm taking some liberties here, but we go with 34.8 and probably can do the full 127. Okay, cool. Yeah, because that 127 angle here, this is actually fixed by the encoder's maximum range of motion, I think. Maybe not, but let's try it. Let's try it. Okay, this is taking too long, guys. I need to speed up. Next angle here. This is probably fine here at 41. We have 45.862. That one doesn't make a lot of sense to me. And then we're just gonna go in the same one here. Doesn't make sense because previously, I mean, was that a typo actually? You know how I was saying equations is the more educated way of doing this? This is what I meant. Yeah, this is a typo. Pretty sure. Anyways, the next step after this is literally running it, so we're gonna know pretty soon if we have if we've made an error. I think we can. Now we're going down, and the other way. I'm gonna keep going 127. That makes sense to me. And then 21.8. I think that's gonna be the same on this side, probably. Oh, that dropped a lot. Gonna play it safe here at 36.8. Gonna keep the same angle everywhere here. Good 32. Probably can keep the same one on the other side, right? I don't see issues there. 31. Yeah, should be fine. Somewhere like there. 32 and 28. These things are not going to be linear, by the way, if that's what you're thinking. We'll give it 25 just to be safe. I'm speeding through it. Just want to get to the part where we can verify results. 21. This is the kind of work that a lot of people would be ashamed to stream, put out in public, because again, this approach doesn't feel very educated. Basically, it seems like I'm guessing here. Which it's actually partially true. There's a lot of guesstimating going on. Yeah, and could this be done better and more systematically? Yes. Am I trying to get back to my day job? Also yes. And am I trying to minimize the time I spent on these? Also yes. But yes, there is 100% a better approach of doing this. And I did say at the start that this is the whole point of reverse kinematic equations. And if you're doing this, I recommend you look into that. But if you're like me, you could also do these. And again, part of me really wanted to do this exact same exercise, but on the leg itself in person, since we already have it all like set up and stuff. But I do think that will take longer. We're moving kind of fast here. So, no. All right, 2 more. I wonder if the haters are gonna comment on this approach. Been getting some hate recently. All I ask is, if you're gonna hate, don't be an anon. Have a picture, show your work, show us why you're better. If you're gonna hate as an anon, like, don't even bother. All right, that's it. So now I have some equations here to okay. And so now I'm gonna ask ChatGPT for help. I'm gonna leave this kinematic sketch there. Let's open back ChatGPT and no, control into servos, yes. I'm going to explain that the angles of servo 2, it's servo 2 in code, servo 1 in the spreadsheet of servo 2 can be any of the following in degrees. I've mapped out the possible angles for servo 1 which do not lead to linkage collision. I would like to cycle the servos through every servo 2 angle and all of the servo 1 angle and the minimum and maximum servo 1 angle for each. We can do one full sweep of servo 2 angles with servo 1 minimums, and then followed by another servo 2 full sweep followed by servo 2 maximums, and then loop through it. So hopefully that makes sense to you guys. The only thing is that I think this was a mistake and the angles can't go that low. That's the only thing. In fact, I'm pretty sure that was a mistake. But let's try it. I'm betting money that that was a mistake. In fact, let me do some quick YOLO math here. But the correction factor, 85 is the maximum, and any other numbers should be over that. And so I'm subtracting the correction. No, am I subtracting the correction? Maybe we should add the correction. Okay, I'm gonna go with it, and I do suspect this will go catastrophically, but I'm gonna go with it. gotta go with it. Trust your instinct. Trust your math. Trust your work. All right. Anyways, code is being generated. So I'm gonna. Well, actually, let's take a look at the code first, but then I'll rotate to the next camera, and you guys can see these fail spectacularly from a better angle. Okay, so defining the max means as a library, as a dictionary, I think. I don't know what these are called in C. An array? That's not an array, I think. Attach servo one. Yes. Okay. Okay. Yeah. 18. I see. All right. Yeah. I think I trust this code. Let's. So let me connect the servo to the Arduino to the computer. We're gonna verify and upload the code. My Arduino cable is not long enough, but okay. Oh, lost my mouse. Arduino Uno does not show on the serial ports. Kind of wish this was wireless or something. There is Arduino Uno. I just had to disconnect the external power source. Verify. I'm gonna just YOLO save everything. It's on ChatGPT anyways, and eventually I'll have a GitHub repo for these. But I'm gonna upload, and after the uploads, I'm gonna switch the camera. So see you guys in a bit. All right, big moment of truth. Here's the thing. Gonna give you a good angle. Yeah. All right, this is the thing, and gonna connect one servo at a time because. No, actually, yeah, one servo at a time. Okay. So it should be sweeping through. Every time this stops, this shakes, which is not my favorite. But so the envelope for this first servo looks safe to me. Right, okay, so now we connect the second servo, and this is where things could be interesting. Watch here, this is where we will collide. Oh, collision. Collision. Okay. All right. Okay. So we got some collisions here, unexpected collisions that should not have happened. I actually don't know how that's even possible. It has to be because of the position of this guy. So just the upper on its own should not collide with anything. It's the position of this guy here, the servo 2, that can lead to collision. So it's coming close, but it's not collision. And so this guy is just cycling through. By the way, we still have a delay. Obviously, it's gonna move much faster. All right, so we obviously need to work on this guy. So back to the computer. Actually, let's observe closer what's going wrong. Oh my god, all right, that was awful. That was really bad. Just getting wrecked. All right, I'm gonna put this on the upper on somewhere close to 0, which is safe for servo 2, and see what servo 2 is doing. Servo 2 is trying to go this way, but it can't, I think. Yes, trying. What can it do? Oh, servo 2 is trying to do something bad. All right, servo 2 is going past its minimum here. All right, back to the drum board. All right, so what went wrong? Remember I was saying like servo 2 should never go below 62. So I suspect something went terribly wrong there. Not sure why. I don't really understand what, but we definitely saw some bad collisions there. Let me just get my mouse back. Team Apple only gave me one port for my mouse and Arduino, so I have to switch them. Rotate, they have to share. All right, so here we are. Of course, at a very extreme angle here. Let's go back to 118. So servo 1 behaved accordingly, the upper, and it was this guy here. Sometimes tried to go this way too much. And this angle we measure as 130. I guess 130 here. No, on CAD, 130. So this is 36 on CAD, so that's minimum, right? So 36, no, that's maximum on CAD here. So these angles seemed fine, I think, fine, but it's the other angle that is problematic. So 123 shouldn't be what it is. So I still, yeah, it's the same thing. I'm obviously messing up my correction factors here. Which is silly because it's probably the simplest thing to do, but the correction factor should be the same for both. So 42.2. Yes, so this is equal to 170, right? So yeah. I'm gonna take a look at the, I'm gonna take a look at the actual like one time. See if I can really grasp what's going on here. Can't even get it to run right now. I don't know what's wrong. Looks like the camera died. Camera is fixed, and yeah, obviously these angles look wrong to me. They should be going the other way, and so one easy thing to do is to flip the angle, to flip the correction factor to go the other way. It's just that I want to fully grasp Y, and I don't fully grasp Y right now. If that makes sense. So yeah. So actually, what I would put here, I'm gonna take some liberties here, but what I would do, trying to reconnect, lost connection. Is Google Drive down? That would be funny. There's no chance. Okay, anyways. So what I'm gonna do is calculate the difference between these two angles. So this one's always gonna be this one minus that, and add it to 85, which I know it's safe. Okay, so that should be it. And then I'm gonna tell ChatGPT that I recalculated the servo 1 minimum angles as follow. Please update the code. And I think this is gonna work. We'll see. And then while that starts loading, I'm gonna get rid of my mouse again so I can connect my Arduino Uno board. And all I wanna see is the leg to cycle without getting wrecked, if that's too much to ask. Okay, so Arduino is on. We update the code. We don't even read it, we just verify it and upload it. And if it explodes, I blame ChatGPT. There's an error. Of course, Arduino is not on a serial port because I have the external power source on. So we're uploading, and I'm gonna switch the cameras again. All right, fingers crossed. All right, here we go. Moment of truth. So all I have to do here is power the Arduino's code is already running. I guess I'm gonna put the external power source on just to get a boost in power compared to my MacBook. So that one's the easy one to cycle. That one cycles just fine. And then we have this one here. I don't know if you can see. I mean, nothing's happening. I need to figure out why. This looks like a healthy position. Oh, it's possible that we were missing a ground pin. Let me check the delays here, because it's taking forever. Delay 1 second. I don't know why it's taking so long. I also don't think, I mean, I don't know if we're running out of current here, but I also don't think the servos are pushing. Against anything too hard. I don't think this can go anywhere anymore here. I don't know if that's what it's trying to do. I think it might be trying to do that. But why would it be? I'm gonna hit reset here on the Arduino and just making a note that it is getting kind of hot to the touch. Very, very hot. Okay. So I just gotta assume that. Okay, so I disconnected servo number 2 and now everything's shaking. Your guess is as good as mine. I have no idea why. All right, I need to better understand what, I need a refresher on what, on what 85 degrees on servo 2 look like and 170 look like. So I'm gonna disconnect that for a second here, and gonna upload new code. And all I'm gonna do is sweep through. Oh, it's still moving. because I just powered it again. But all I wanted to do is to sweep through servo number 2. Servo number 2, 170 degrees to 85 degrees, just so I can see it. So the servo number 1 is not even going to move here. All about this guy here. So this guy, we'll zero it. That's about as zero as you can get. Oh, I forgot to power it. My bad, guys, my bad. There we go. So these guys should be moving. It is moving. Tiny, tiny steps. I think it's doing 1 degree at a time, between 1 second. I'm also going to tell it to print the current angle to the serial monitor. Can you also print? And I'm going to increase the speed to 5 degrees per second because it's a little too slow. We're going to get to the bottom of this real quick. All right, verifying the code, uploading, and let's see. Oh, I'm going to open the serial monitor. Serial monitor is just like a. Okay, so that's 140. Actually, it might be in the wrong serial monitor. I don't know what block rate we're on. Oh, 9,600. 85, 170, 865. Yeah, okay, so okay, so 40, 130 degrees, 120 degrees, 100. So really, okay, I got down to 85 there and all the way up to 185. Or so it's 185 to 85. It's obviously a safe operating margin for when servo 1 is almost at 0. But if we take off the power here and then we move this guy somewhere else, we start to get a collision here. So we gotta start moving. So obviously, as this upper goes down, when we should expect that 85 value to go higher, and really, and I guess that the 85 value to go higher and the 185 also to go lower, and so the range of motion of these of servo number 2 as servo number 1 stretches should be lower. So is that what we see on the CAD? Let me take another look. But now that we understand that that's going to help, we should be able to move faster. So let's go back to the computer. All right, so now it's clear that me, by trying to save time and cutting corners and just not doing it properly, I'm actually spending more time on these. But should I edit this and remove it just to save my honor? No, I'm gonna leave it here. Hopefully, you can learn something from it. And so what we just learned is that I'm going to write it down here, but as servo 1 stretches, quote unquote stretches, the range of servo 2 is reduced in both the upper and lower boundaries, right? So servo 2's lower boundary is 85 degrees. As servo 1 stretches, that number should go up, which is what we're seeing here, and the upper boundary is 170 degrees. As that number as servo 1 stretches, that number should go down, which is I would argue that's exactly what we're seeing here, but I guess not enough, right? Yeah, not enough. Yeah. So obviously this cat exercise was wrong. So I mean, one way of doing it, like we don't know how far wrong, like if we're wrong by a lot, basically, right? So well, let's take the extreme scenarios. So this is the extreme scenario, fully stretched servo 1. And for a fully stretched servo 1, our servo 2 calls for 141 degrees, which is which this guy doesn't even want to go to, I think. Or on cat is 14. On cat looks like 62. And so fully stretched servo 1. Yeah, I don't think 62 is possible, just testing here locally. That's because our cat doesn't have good collision controls. Okay, you know what I'm gonna do? I'm gonna do it the old way. I'm just gonna cycle it manually, and yes, it's gonna take forever, but I know it's gonna be 100% correct. So I want to leave on these cat exercise just because kind of like everyone can learn from it, but I just wanted it to work. So so first of all, let's find a code that actually works. So this one cycles, this one doesn't work. Let's pull the file from last night. I'm keeping it real here, guys. I made a dumb mistake. Not that there's any glory to that, but I'm gonna move to the other camera now. All right, here we go. So same approach. Cycle it and write down the angles on a spreadsheet to build a lookup table. And once again, the actual way of doing this is reverse kinematics. Should I just go and do that? So we have servo 1 upper and servo 2 in servo 2 max. And we're going to start servo 1 at 0. And I know the top boundary for servo 1 is 85. We know that from the other night. And we're going to cycle every 5 degrees. And I also need to get rid of my mouse so I can connect my Arduino. Yes. All right. Now I want to write new code here. Verify the code. Whoa. I don't know why that happens. Don't do that. initialized servo 1 at 85 degrees, so fully stretched. That's where servo 2 has the least freedom, and that's why it was probably colliding. This is all cold, probably. Dude. Yo, come on. Oh. Oh, I see. Looks like my servo crashed as I was uploading, probably because of overcurrent. Verifying and uploading. Okay. Wait for the done uploading. It's done uploading now. Okay. So this is. That is weird. Servo 2 has been a huge downer. Okay, this should be 0. No. Oh, I see. I have 2 servo 1 writes. I see what's the issue. Coding issue. Alright, so this should be 0 for servo 1, and then if I connect servo 2, this should be 85. And 85 is as low as it can go. So we're gonna start our lookup table here. So for when servo 1 is 0, servo 2 can be 82, and I think we said upper boundary can be 170. So let's try 170. And that looks fine to me, right? So that's fine. All right. So next, servo. So we're doing 5 degrees on servo 1. So servo 1 5 degrees. This is again. This seems fine. Yeah. So that's 85. And then we're gonna try 170 on servo 2. Seems fine. That's cool. Okay. So next, 85 and 10. I'll be surprised if this is actually faster than CAD. So 85 and 10 looks fine. 85 and 170. Sorry, 170 and 10. I don't hear any suffering. Looks good. 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 Let it play, but good. So 85 and 15. I really hope someone comments in the comments and says like, oh, you're doing this all wrong, this is a way better approach. Because that would save so much time. I'm sure there's better ways of doing this that I haven't thought of. So 85 and 15. Okay, yes. 170 and 15. Yep. One way of seeing it is like, oh, it's so far it's passing the test. The other way of seeing it is like, oh, I have more range of motion to squeeze from those previous angles. So I did a misclick here. I put 29 instead of 20. And we're hitting some limit. I can hear it. When the servos go over current, there's like a loud pitch which you can hear. So this is 20 and 85, and you can see it's fine, but we're starting to reach the limits here. So now 170 and 20. This one's completely fine. Next 25, and I don't think 25 and 85 are gonna go along, get along. But let's see. Alright, that's fine.
170 and 25. Also sounds fine. You know what? Looks like we can do push more. I'm gonna go with 175. Yeah, 175. All right, next one is 30, which I basically know for a fact that 85 is not gonna work, but I'm still gonna do it. Yeah, I can hear it. It's not happy. I'm gonna take it down to 80. So can I give it a 5 degree slack? Sorry, 90. I made it worse. Should go up, not down. All right, that's better. Yeah. Seems some hints of collision here. Let me try 95 just to be safe. Like I said, these things are not linear, so. Yeah, that's better. It's still starting to touch. Just gonna give it 100 just to be safe. Yeah. Here's some loud pitch noises. I don't know why. 100. Giving it 100 for 35. Oh, for 30. Sorry, for 30. And then let's try 175 upper range. Oh, yeah. Okay, up to 35. So we're gonna do 135. Yep, safe. Pushing it, but safe. 175 here. Yeah, enough clearance. Up to 40. 40, gonna start at 110 because I already saw that we're in a critical area here. Yeah, okay, some clearance there, 110 for 40, and let's see if 175 still good. Uh, 175 still good. So now 45 and 120, 110. Let's see if that works. Third collision there. Gonna give it 115 to ease it. I say it's still touching, so just for comfort, we're gonna go 120. Oh, much more comfortable, guys. And then the other one, let's test the other boundary at 175. Yeah. We're halfway there. 50 degrees at 120. 120. See what we got. I'll call that collision 125, just to be safe. And 175. Yep, still good. 155, sorry, 55 degrees now at 125. Collision going up to 130. That's fine. And now 175. Yeah, there's gotta be a better way of doing this, right? There's gotta be.
Maybe as soon as I'm done, I'll be like, oh wait, why didn't I do that? Gonna start 60 at 135, following the trends. And that was a good call. 135 for 60. And then 175 has been working just fine. Yep. 175. On to 65. 65, 175. No change whatsoever. Why would it change? And then 135. Looks like a collision, minor collision, going up to 140. Much better. 140. Up to 70 now. 70, 140. Too tight. 145. 145 is good. And trying 175, which obviously is gonna be fine. But we should think of why is it fine. You see how much play is on this thing? We're gonna fix that. Don't you worry, guys. We're gonna fix it. 75 at 175. Pretty good. 75 at 150. Yeah. 80 at 150. No. 155 for 80. Yeah. It's rubbing. I know it's gonna wear over time. 175 for 80. Getting close, finally getting close. And last but not least, 85. And 85 and 160. Let's try it. Oh. 165. Yeah. 165. 175. All right, I'm happy. Okay, so next, let's combine this into one smooth angle. So I'm just going back to ChatGPT here. I'm telling it I recalculate the angles. Honestly, that was pretty easy. I think I should just have done the physical stuff first. I just thought, cat first, a little cleaner, smarter. Trying things like these, trial and error, always feels a little amateurish. But I guess I shouldn't hide the fact that I'm just here to do whatever it takes to make it work. All right. Here's some code. Let me actually read the code here. I want to get rid of the delays. Well, I'm not going to completely remove them. I'm just going to reduce from 1 second to 0.1 seconds. Open serial monitor. All right. You're going to upload. We should see beautiful motion. It's jerky because of the delays, I think. So if I remove delays, I'm going to completely remove anything that says delayed, the word delayed. So the other reason why it's tricky is because we're commanding angles at 5-degree increments, and so it's not as smooth. And so ideally we can extrapolate in between. This seems like a common issue, so I'm sure there's something for the. So ChatGPT has come up with an interpolation. I'm down to try it. I think that's the issue at least. I mean, that makes sense to me. Obviously the delays were also not helping, but I already removed those, so. I think the code is uploaded. Still very jerky. I think I'm wrong on smaller steps are not as good. I mean, on the bright side, there's no more collisions, right? So that's good. But I want a smooth, quick motion. Alright, so ChatGPT says take smaller step increments, so say like 0.001 degrees. Use a smooth motion function that continuously increments or decrements the servo position. Use micros for timing, but that's for delays. Okay, so. Alright, we're gonna test that code. Not super familiar with the servos library here, so I'm learning live, but whoa. This is not how I would want to cycle it. So I don't think this is representative, right? We'll never walk like this. We cannot walk like this. But when it goes, from one end to the other, there's actually very smooth motion. That's the kind of motion that we want. Alright, the code. It's even slower. Alright, so one of the improvements that ChatGPT is recommending is basically instead of having one server to wait for the other to run them both parallel. I don't think that's going to do a huge difference, but let's try it. It definitely helps. But I feel like there's got to be something else here that we're missing. Yeah, well, okay. So every tiny movement represents basically one loop. We're running a continuous loop. And that's I'm not super happy with that. So the servo motion seems to be smoother when we take big leaps instead of small fractional degree increments. With these in mind, how can we adapt the code so that the servos move faster? Okay, so it's basically saying go back to taking bigger steps, this time 3 degrees at a time. We started at 5 degrees at a time and it was very jerky. So we might need to go Google some stuff because I don't think ChatGPT has a good answer. Upload a new code. Is that faster? I think so. Is that super jerky? Yes, for sure. I want to increase the step size to 10, which is, we start at 5, so 10. Well, definitely faster. Very jerky. I mean, if we run like this, I wouldn't be surprised if this breaks. I'm kind of curious what breaks first, though. All right. I'm gonna call it a day there. I think we've reached our target in a way. I'm gonna go do some research on how to smoothen this motion and only then cycle it. But basically on this part 2 video, I think we assembled a leg and got it moving. and learn a lot about how to avoid collisions and stuff like that. So pretty happy with the progress. So yeah, smoothing the motion, and we also have 9 more servos coming, so we'll have the full legs. So we also need to start cutting the body, and also need to build legs to mirror, and then like we'll have like a small assembly process to make 3 more of these. We'll probably need to revise some things. Like I said, I think there's a lot of room for improvement in the fits and overall just, you know, how things, how sturdy it feels. So lots of work to done. But I don't want this video to be, you know, like hours long, which it already probably is like 2 hours long. But thanks a ton for watching, and yeah, we'll continue to make progress, learning a ton, obviously making a ton of mistakes, but I think that's the kind of content that I hope people enjoy. So I'll see you next time.